So hello dears, good morning and welcome back. So we are discussing the mathematical foundation of robotics, and very important topic we are currently discussing is execution level control. Okay. And you see, the other day we were discussing, suppose uh, I have a block. So at every instant of time, I want that at T1 the block will be at x1, T2 the block will be at x2, like that. Tn block will be at xn. So how to achieve that? To achieve that, we will have to actually control this block, right? Mass spring damper block. So this is damping coefficient C, this is K, and this is M mass. So what we have done here to achieve this goal, that wherever I want, the block will go there. To achieve that, I have added a force F. Okay. And you see, now I am designing the servo control. It is called servo control. So what I am doing? So this is my system, mx double dot plus cx dot plus kx, right? So I am just exciting the system with my force F, positive force F. Okay. And I am just taking the state variable x dot from the system, because as a result of just imparting F, there will be some dynamics of the system, right? The system displacement will be there with some velocity. So these are these parameters, state parameters. And M, C, K, they are called the system parameter, and x dot, they are called state variable, okay? M, C, K, in time invariant system, they are constant, okay? So variable is state variable x and x dot. So what we have done, we have taken this, okay, and with some gain parameters, okay, I am just multiplying. So here, this is x dot kv, this is x kp, and negative feedback we have given, which is very common, okay, for stability. Normally we give negative feedback. So F has been designed to be, so in this junction block, which is summation block, so these are the two input signal, which is minus kv x dot minus kpx. So let us call it 1, and then if we take here, so you are getting a x double dot plus c plus kv x dot plus k plus kp x equal to 0. And we told that this is constant, gain parameter is a constant, c is a system parameter. So let us call this c prime equal to c plus kv, and k prime, say, is k plus kp. So the equation 2 from 2, what we are getting? Mx double dot plus x dot c prime x dot plus k prime x equal to 0. So this is again second order. So I have reduced it, although I have excited it with this, and I have designed a servo controller. Incidentally, this is called proportional derivative control, because I am taking action based on system's velocity, proportional to the system velocity, that is proportional derivative part. So derivative part, and this is proportional to the displacement. So this is proportional kp, proportional gain parameter corresponding to proportional part, and kv is a gain parameter corresponding to the derivative part. That's why this is called PD, proportional derivative control law. Control. Okay, so this is the control law which we have defined. So this is, and then after this defining this control law, again I have reduced my system with control to another system as if it is not excited. Okay, so right hand side 0, and then what is my desired expectation from the controller? It should be critically damped. Why? Because the moment I am asking it, so this is t, say t, and this is x. So the moment I am asking at t1, move x1, right? So it's just like step. At t1, move x1. So it can start from 0, and exactly at t1, it should have. So this can be achieved through critically damped controller. So we do not want my controller should be like this, because then at time t1, t equal to t1, it will take more than t1 to reach this one, or I do not want also over damped like this. Okay, so these fundamentals you perhaps understood from my earlier lecture. So that's why critical damping situation is very, very important, and critical damping condition So from critical damping condition, what we are getting, C prime square equal to 4 m k, right? So C prime equals to 2 root over of m k prime. Now, take an example. Let us take an example. Say my system parameter m equals to 1, c equals to 1, and k equals to 1. All the system parameters are equal to 1. And then I need to determine Kp and Kv. So what you are going to get, C prime, this is 1 plus Kv equals to 2 root over of K means 1. K. Okay. Now let us select that, okay, that K prime, say, so this is controller design is an art, as I told you, no? Say K prime equals to 16, okay? Now, why I did that means I can take any value, but I will have to realize that in actual practice, because this is designing a system, right? So then what you are going to get, if you select K prime equals to 16, then C prime will be equals to twice 2 into 4 equal to 8. So C prime equals to C plus Kv, C equals to 1, so that will give you Kv equal to 7, and then K prime equals to C from here, K plus Kp, that will give you K equals to 1, so Kp will be 16 minus 1, that is 15. So these are my gain parameter, right? Values Kp, Kv. Now if during realization, if you see, oh, this 7 and achieving 7 and 15 is not possible, then again you will have to go there and see, okay, instead of 16, maybe I will do something else, okay, 25, okay, and then again redesign till suitably you can, because these are to be realized, right, in practice. So till suitably, conveniently you can produce Kp, Kv value, you can go ahead and select. Okay? So that's why up to this mathematics, conceptual, and then empirical, the selection, you on as a designer on the driving set. So this is okay. So you have got, and if you just keep do this, plug in this value, theoretically, let us assume that I can um, actually generate these values, and then if you Kp and Kv, these values are plugged in, then what you will have, you will get system critically damped. So wherever you want that at time 2 seconds, the system will be at 2 centimeter, and you will see exactly with this, it will go there. Okay, so that's the remarkable achievement you have. But one bad thing about this controller is actually, you see, the control gain parameter actually are clubbed here. They are the integral part of the system. So C prime contains a system parameter C and a gain parameter Kv. System parameter K and a gain parameter Kp. So Kp, Kv you are designing, but they are clubbed with system parameter. So what is the problem? Problem is, as far as this mass spring damper system goes, no problem. But if having some different values of K, M, C, okay, so if you want that I will design a controller in a modular form so that I can plug out from one system and another second order system, I should be able to use the same controller. That is not going to happen, and that's a bad thing actually. Why? You understand, right? That we'll spend a lot of money in designing the circuitry, which will give me Kp, Kv value as per my desired value, and they should be independent of the system parameter, so that just we can plug out from one system, plug into another system, it should be able to control that system as well. So that facility is not there, okay. So we will try to modify this this control scheme, servo control scheme, to this one, which is called model based control. It has so many names. In robotics domain also it is known as computed torque control, okay, because you see torque in revolute giant motor produces torque, and same principle we apply. So we need to understand what is that model based control. So let us consider again the same system, mass spring damper system, okay, and here what we have done is, you look very carefully, I have taken x dot, and in a separate block I am just computing this Cx. So my equals to if, now I will just do some trick. What we have introduced some parameter alpha and beta, you see, and if prime, this is, and this is actually servo part, servo control part, and this is actually model computation part. You can calculate, you can call it, this is not a servo part, means no control you are doing here, okay. So what we are doing, that model updating part, model parameter updating part. So this is model parameter updating. So entire control I have divided into two parts. Very carefully, you see, very easy. One, the total force F actually is now composed of two. So this is actually alpha times A prime plus beta. Okay. So here what we want, this beta is equals to plus kx, and let alpha equals to a, right? So then what is my system with control? System with control is becoming m x double dot plus cx dot plus kx equals to alpha, means m f prime plus cx dot plus this. So now see what is happening. This cancels out. This cancels out. M divide by m both sides. Then f prime becomes. So this is the trick, great thing we have done. What we have done? System is attached with a control force F, and it has now two parts, fragmented, right? One part is dedicated, beta is dedicated for updating some of the parameters which trivially we know. Okay, you see what we have done here, C, K, so that's why it is called model based control. So once I have the model, I know this Ck dot plus Kx, okay, and I am taking that signal x dot, and moment x is there, x dot is there, I can compute, Ck is known, I can compute. And once I compute, I am putting that computed value to this junction block. Another part, which is actually servo part, like here, so everything was servo control here. So this part only are servo control. So I am taking that same x dot, and now these are my two gain parameters. So what is the signal here? Kp, x, kv, x dot, they are minus, okay. So I can now see that, and tactfully putting m here, okay, this signal is actually m a prime. So here it is coming, actually plus what I have written, right? So this is a signal here, m prime plus cx dot plus kx. So these are the input signal to this junction, output is f equal to f, which we have written over here. F in place of f, we have written. So this is the exact schematic diagram. And you see here, same x dot, and then what you are getting over here, input signals minus kv x dot minus kp x. This is equals to, see, minus kv x dot minus kpx, right? So this thing I am controlling all day, and this becomes, so if I plug in to equation 5, then what it becomes? Putting this value in 5, it becomes x double dot plus kvx dot plus kpx equal to 0. So this is actually control law of the servo part, which is very, very simple, as if you are controlling a unitary mass system. You see, there is no system parameter in this control law. Here there were system parameter m, c prime, k prime, but here no, only kp, kv, and nothing else, right? So now you can again put critical damping situation, consider critical damping condition from 6, you get what we get. That is kV equals to 2 root kp. Huh? Isn't it great? See, now I have much more freedom than this. Oops. Or than this. We had earlier this. Where you require to know the system parameter. Here I do not require. So directly I do not require to specify that what system I am going to actually control. So you see, actually, if now same, so if m equals to 1, c equals to 1, and k equals to 1, then everything I can compute, right? So what is your alpha? Alpha equals to m, alpha equals to 1. What is your beta? X dot plus x. Like that. So you can compute alpha beta, you can compute, and then you can select any kp, okay, kp, select, let kp equals to 16, and immediately kv will be equals to 8. Or if you do not want 16, you put any value, and very easily you will be able to figure out kp, kv. Those are the gain parameter, and those are the actually controller requires those gain parameter, and they will determine how the controller will perform. And the one beauty is I can just plug it out. This part is the actual control, servo control, right? And I can, and these are actually merely upgradation of the system parameter. And this is, that's why it is called model-based control. It will be very effective in those areas where really you have a very good idea about the model of the system. Even if you do not have idea, some parameters you will have to identify, and you can decide that how simple I can make my controller. But your again objective would be, can I reduce the controller for controlling a unitary mass system like this? So for that you require model, right? Understanding the model. And if you identify, okay, these are the parameters, unnecessarily I will not try to control them, rather I will try to just upgrade them. So this is parameter upgrading, upgradation is taking place in this part, and only in this part actual control is taking place. The idea is this will make the controller design simpler. Not only that, it will be modular, in the sense that this is, since it is is controlling a unitary mass system, this can be plugged out and plug in to another system, and same performance. If you want critically damped condition, means at t equal to 1, it will be x1, t equal to 2, same performance will be achieved. So this is the concept of model-based control. Why it is called model-based? Because it is based on the model. Some part of the model you need to know. If you do not have any idea of the system and you cannot model the system, then this control strategy will not work. But if you know, and in case of robot control is actually at the joint level is a motor control, and motor model is well known, right? If you know that, then you can actually utilize this model-based control. to simplify your control. Not only simplify, you can make your controller modular in nature. So this is, I will give you, I will just stop here after giving a very common example. Okay, it's not similar, but this will help you to grasp the idea of model-based control. You see, suppose I have a TV remote control, and I know I want to see, I need to watch a particular channel. So I have two options. Number one, I know the channel which I am going to see, it is somehow in between, well, 78, 79, right? In the vicinity of that. So what I can do, I can go to up to 77 directly from the remote control, and then fine tune. Is it at 79 or 78, like that. So this is model-based control. For that, you need to have an idea about that, where the channel is. Otherwise, it will not work. Otherwise, what was the option? Option was right from channel 1, you go on searching, okay, the particular or desired channel which you want to see. So this was the option, which is a bad option. But if you know, for example, first time, second time, you have already watched that particular channel several times. So go in, but you are not remembering exactly what is the number of the channel, and it happens actually. But you remember it is beyond something 70 or like that. So you go straight way up to 70, because that's the model parameter upgrading, analogous to upgrading the parameter. You don't try to control. Only you are controlling, seeing the channel, hand-eye coordination, and fine manipulation you are doing for the that unknown part which is required. So more information, more accurate information you have, more or less control, fine tuning will be required. Rough idea you have, you may need to make larger fine tune. Okay, so fine tuning is costly because it takes a lot of time. So this is the analogy I thought that I will give you. This is actually the concept of model-based control. So if you have a model, you decide, okay, these are the parameters, just I will take the output signal, actual signal, and I will try to update. I will not try to control. Rather, I will try to control those, I'll control those parameters, which is gain parameter, right? And I will reduce my controller design to control a unitary mass system the way we have done it here. Okay, so those who still want some clarification, you can study book, right? We have two textbook, Peter Cork and Introduction to Robotics, John J. Craig. So these portions you can get further information there. So with this, stay safe, have a nice day, bye-bye.